Now, conditions of overturning. When our vehicle is moving on a curved road, there are chances that it may overturn. So the outer edge is always raised slightly. Number one. Number two is that normally when the body is moving on a circular track, we find that friction provides the centripetal force for rotation. So this fact is to be applied in the condition of overturning. We shall find the condition for the car to overturn. That is, under what circumstances the car moving on a curved road will overturn. Suppose the distance between the centers of the wheels of the car be 2a and center of gravity is h meters above the ground. The different forces acting on the car are shown in the figure. The weight mg of the car acts downward. Obviously, weight is acting vertically down through the center of gravity g. The normal reaction of the ground on the car will be R1 and R2, that is on the tires. So the normal reaction of the ground R1 and R2 on the inner and outer wheels respectively, these acts vertically upwards. Suppose the force of friction is F1 plus F2 between the wheels and the ground towards the center of turn. Suppose that the radius of circular path is R and the speed of the car be V. There is no vertical motion, therefore equating the vertical forces we have. So again the same figure is there. The reaction of the surface on the tires will be R1 and R2. F1 and F2 are the forces on inner and outer wheels. mg is the weight acting vertically down. And A represents the acceleration. Now two figures are indicated. In one case there is slight tilt. R is not equal to 0. So we find G is the center of mass and H is the height. F2 is the force acting on the inner wheel, whereas outer wheel is slightly overturning, trying to overturn. The value of R1 plus R2, that is the total normal reaction, will be the weight. The horizontal force, that is equal to centripetal force for the motion in a circle. Therefore, F is equal to F1 plus F2, and this total force provides the centripetal force, that is mv square over r. So we have formed two equations. One is with F1 plus F2, other is R1 plus R2. Taking moments about the center of mass of the body is G. So F1 plus F2 into H plus R1A will be equal to R2A. So we have utilized the two normal reactions and we should get the value of R1 minus R2. Then we will generate two equations, one R1 plus R2 and other R1 minus R2. They will become simultaneous equations and then individual values of R1 and R2 will be calculated. So in the last line we have gone through, that is F1 plus F2 into H plus R1A equal to R2A. F1 plus F2 will be equal to R2 minus R1A over H. Now this is the third equation. So we are finding the first and third equation, R1 plus R2 is existing, and in the last one it is R1 minus R2 is existing. Combining this with equation number 2. So wherever it is written F1 plus F2, we can replace it by R2 minus R1A over H. And we'll continue with the calculations. R2 minus R1 will be calculated as H mv square over R square. So we have two values. One is R2 minus R1, other is R2 plus R1. These are the simultaneous equations. So if we add the two numbers, one variable will cancel off and the value of other variable we will calculate. We now have two simultaneous equations, that is number 1 and 4 for R1 and R2, solving these by adding and subtracting. So in one case, R2 will cancel off, in another case, R1 will cancel off. So we can get the two values. 2R1 will be equal to mg minus hmv square over AR, and 2R2 will be mg plus hmv square over AR. So to understand these equations, it is very necessary that a slight portion of 11th class is to be slightly revised, where we have discussed about the simultaneous equations, or in 10th class. From these expressions, it is clear that inner wheels will leave the ground when R1 will become 0 and the car begins to overturn. Now, mg is equal to, that is the weight, will be equal to hmv square over AR. So, the limiting speed is given by v square is equal to gra over h. That is what required. Now, we will go through with kinetic energy of the rolling motion. If the body is rolling without slipping, how much is the kinetic energy? Total kinetic energy of the system of particles about the fixed reference frame is equal to the total kinetic energy of particles with respect to center of mass plus kinetic energy of center of mass with respect to the fixed reference frame. The kinetic energy of rolling body can be separated into kinetic energy of translation and kinetic energy of rotation. So, kinetic energy of translation, the formula will be half mv square, and for rotational energy, we have derived the formula earlier. You can see from there, and k, that is the radius of gyration, will be estimated by function half I omega square plus half mv square of the center of mass. Substituting I equal to mk square. So wherever we find I, we can substitute the value mk square, where k is corresponding radius of gyration of the body, and vcm means velocity of the center of mass, that is equal to r. We get k is equal to half mv square into 1 plus k square over r square by putting above values. Now, in our next example, we consider a ring, a solid cylinder, and a solid sphere, and all of them are rolling on the same inclined plane. When they are rolling without slipping, we have to find which of the bodies reach the ground with the maximum velocity. Now, in the figure, it is shown that there is an inclined plane, inclined at angle theta, and the ball is at the topper portion, and when it will be released, it will come to the down corner. So, h is the height of the plane. Now, the potential energy lost by the body in rolling down the inclined plane. Whenever body is rolling down, there is slight loss in potential energy. That is, there is slight loss in mgh, and whatever is the loss in mgh, same will be the gain in kinetic energy, because total energy remains constant according to the law of conservation of energy. Since the bodies start from rest, the kinetic energy gained is equal to the final kinetic energy. Now, we find that from equation, radius of gyration k is equal to half mv square into 1 plus k square by r square suggested earlier, where v is the final velocity of the center of mass of the body, equating k and mgh. When we say we are equating k and mgh, we are putting the value of k and then we are equating with mgh. So figure remains the same. Now we find mgh is equal to half mv square into 1 plus k square over r square, or we can get the value of v square from this equation, cancelling m from both sides. Now for a ring, k square is equal to r square. Velocity of ring will be 2gh over, that is 2. And 2 will cancel off and the equation will become under root gh. For a solid cylinder, k square is r square over 2. And the velocity of the disk will be 2gh over 1 plus 1 by 2, and the expression becomes under root 4gh over 3. Now we come toward the solid sphere. So there are three different cases we have considered: a ring, a solid sphere, and a solid cylinder. Now for solid sphere, the square of the radius of gyration is r square over 5, and velocity of the sphere will be under root 2gh over 1 plus 2 by 5, simplifying the equation, and that will become 10gh over 7 under root. From the results obtained, it is clear that among the three bodies, the sphere has the greatest and the ring has the least velocity of the center of mass at the bottom of the inclined plane.